Welcome, everyone. Good afternoon. My name is Elissa Strome. I'm the Executive Director of the Pan-Canadian AI Strategy at CIFAR and also the Associate Vice President Research. And it's my pleasure to welcome you all today to CIFAR's webinar on Science is the Exit Strategy. This is a new series of webinars that we're offering to share with our community research that's going on by CIFAR researchers, fellows, Canada-CIFAR AI chairs in Canada and around the world to share how science and science-based decision-making can be used and is being used by governments to help us think about how we can reopen the economy in the wake of COVID-19. If you're not familiar with us, CIFAR is a Canadian-based global charitable organization, and we convene extraordinary minds to address the most important questions facing society and humanity. Like many others across the globe, CIFAR has pivoted quickly to take action on COVID-19, and we've done a lot of work in the last 9 weeks to mobilize researchers across Canada and around the world to help them and support them advance research on COVID. What I'd like to do today to kick off is introduce you to two researchers that we work with at CIFAR. Marzyeh Ghassemi is a Canada-CIFAR AI chair at the Vector Institute and assistant professor at the University of Toronto, where she also holds a Canada Research Chair. Her work focuses on applying machine learning to understand and improve health. Joseph Paul Cohen is a postdoctoral fellow with Yoshua Bengio at Mila in Montreal and at the University of Montreal. His work examines the applications of AI in medicine with respect to computer vision, genomics, clinical data, etc. So Marzyeh and Joseph have a new collaboration that has emerged as a result of COVID-19 and them thinking collaboratively about how they can work together to address some of these issues. Their project will use AI to develop approaches to understanding COVID-19 based on chest x-rays. And so we're going to explore, and other types of medical imaging. So we're going to explore their project a little bit more. Before we begin though, just a few sort of housekeeping issues. The session today will last for approximately 30 minutes, and I'm going to sort of kick off the conversation, but then we'll open up the floor for questions. So we would love for the audience to send in your questions. Please use the Q&A function. And not the chat function, because we'll be sort of monitoring your questions that come in through Q&A, and we'll make sure that we save plenty of time for those questions. And lastly, I just want to let everybody know that this session is being recorded. So if you want to go back and look at it later or send it along to your friends, we'll have it up on the CIFAR website early next week. Okay, so let's begin. Marzyeh and Joseph, thank you for joining us today to share your work and to be part of this conversation. Let's start, Joseph, by talking a little bit about the work that you did last year. You built a platform called Chester, sort of ironically named, an AI chest X-ray radiology assistant tool that your team developed. And now you're pivoting and thinking about how to apply some of that work and the knowledge and tools that you created towards COVID-19. And so the first step in your project with Marzyeh is to build a public data set of chest X-ray, CT images, maybe other medical images as well. And so how are you guys going about doing that? What are the steps you're taking, and what are some of the challenges that you're facing?
Yeah, so initially we had this Chester tool, and it already predicted pneumonia, given data that existed before from like the NIH, MIT, Stanford, and we wanted to see does this work on the COVID pneumonia cases? Is it able to offer an assistance there? And we looked around for what data to try this on, and couldn't find any. And we contacted a bunch of groups, and it seems very difficult to get data from hospital groups. They're also very busy, and hospitals that aren't busy don't have any data yet or didn't have any data at that time. So it was really difficult to get a handle on all this data, and it seems like the infrastructure in the hospitals was not, able to get us this data. There was no infrastructure in place to allow researchers access to data as it's happening, right? So this was unfortunate for us there, but we found that journal publications did have these images in them. Researchers were publishing like 1 or 2 patients at a time in these publications, and then publishing them, these high resolution or kind of high resolution digital images on the journal web pages of like Radiology and the Lancet, right? So in these online publications, we can access a digital version that's actually pretty high resolution compared to what these models were trained on, because we would resize them to be pretty small images, like 224 by 224 resolution images. And the images on these websites were thousands by thousands, right? So we had like a sufficient resolution there. So we just started aggregating these images into a data set we could work with by manually going to each web page, downloading the image, and then reading the publication and finding the different kind of clinical outcomes and the different attributes about these patients that were already published there. And this was really good for us because the ethics and consent were already taken care of before this paper was published, right? So that made it very easy to work with this inside the ethical framework of the University of Montreal, because if it's already public and it's already had all this consent done, we can use it. So we could get going right at the gate with all these images, right? So this allowed us to start building up this data set, which is we now have hundreds of frontal chest X-rays from different patients, right, with multiple time points.
Great.
Of those patients.
And from around the world, I guess, too.
Yeah, all over the world, which is a good way to validate these models, because we don't want to just have one hospital that could have an artifact that makes it just work there but not other places. So we can really test tools this way, which has been often how this data set has now been used by a few groups, where they have their own internal data set that they make, and then when they actually go to validate their model, they do it on an internal data set to really prove that it will work, because they can have a balanced cohort that's like nice and randomly sampled. But then they can publicly use the data that we put together to demonstrate that their model is working, right? So this has been good. And beyond publications, we're also looking at these repositories that exist. There's a EuroRad system, which has been phenomenal as a resource because their licensing is very clear for us to use for research. So these different repositories that have been put up that they're kind of silos themselves of these COVID chest X-ray cases, right? So not only do they have chest X-rays, they have CT slices. Some of them have CT, like full CT volumes. So there's this massive data that's tucked in all these different systems all over the world. And where we've been slowly putting it together into this data set. And then from the small data set, we can start training these models.
So it sounds like it's a very labor-intensive effort just to even build the data set in order to be able to build the models and then go on further and do the research.
Yeah, it's very hard to build automatic scrapers. We've had some automation in this. We just got some good results on our EuroRad automatic scraper. So we can scrape a bunch of the detailed, like the images, we can get them properly scraped with some basic metadata. But clinical outcomes are really hard to scrape from natural text that radiologists are writing, because you don't know if it says that they tested for COVID and it was negative, or that they tested for COVID and it was positive, right? So that the way it's worded can be just wild. So the best thing is to just have a human read it. So we've been doing that. And we have dedicated students and like people looking at these things. And I've spent a lot of time staring at these reports and learning a lot about, I feel like you really learn more about the disease by reading a bunch of case notes from doctors all over the world, which scared me a lot. So just reading these case stories are very, sometimes sad.
It brings it home a little bit, makes it a little bit more real, right? Great.
Oh.
Okay, so Marzyeh, I know that a key objective of your project is to develop some new machine learning algorithms in order to be able to analyze these these medical images that you're aggregating across many, many different sources. And so why and how is that challenging? What are some of the challenges that you face? And particularly from the fact that these images are being compiled from so many different sources in different modalities, in different languages, maybe the case notes are in different languages. What are some of the challenges that you have in actually developing the AI tools once you've got the data set together?
I think there are a couple of things that make this very challenging. I think that the first thing to sort of keep in mind is we know from work at NeurIPS, one of the large machine learning conferences this past year in December of 2019, that medical image statistics don't follow natural image statistics. Right, so one of the reasons that convolutional neural networks are so efficient at doing object detection or classification or any of the other many tasks that they they work fantastically well on, is because there are these natural image statistics, and there are things that you can assume in many cases about this modality, right? So if two things are close in pixel space, right, they're either close in real life or there's a border there, right? And those kinds of assumptions don't work in, you know, imaging modalities in the same way, right? Because it's not actually just a natural image. And so we know that there are differences in how you may want to fine-tune or take pre-trained deep neural networks and apply them to medical imaging. So that's its own challenge in its own right. There's also a lot of, you know, uncertainty about differences in, you know, severity of cases and also labels for cases, right? So one of the projects that one of the postdocs in my group was looking at, she's looking at these labels that are shared and in some cases not shared between large chest x-ray imaging data sets. So these are data sets that are put out by MIT, by Stanford, by the NIH. And they have some overlap in some of the clinical labels that are assigned to the images, but it's not complete. So some places will label for, you know, a particular condition, a pneumothorax, and others won't. And this also reflects differences in what those actual care centers tend to specialize in and the populations that they see in general. So those, I think those are very challenging because again, when we develop models in the natural world for things like, you know, object detection. We know object detection is important because humans do it. It's a task that humans do. And we know that a dog is a dog is a dog, right? We can argue about what breed of dog and how old the dog is, but we all agree that this is a dog, right? And you could take an untrained human, not a specialist, not somebody who has gone to medical school for a decade, and every untrained human will agree that this is a dog, right? But you can have two expert radiologists who have gone to school for decades, and they will disagree about the label that should be assigned to this image. So this is also incredibly challenging for machine learning models to operate under. And then finally, one of the things that's really challenging specifically in this setting is that this is a novel condition. And that's something that we're trying to wrap our heads around in terms of how to do what is called few shot, meaning I see a few examples and then I'm quickly able to generalize, or zero shot, meaning I've not seen any examples of this particular condition, but I'm able to detect it as a new condition. And these are specific regimes in machine learning, but they're often, when you use these specific regimes, often it's in very controlled environments where you promise that you'll only show the algorithm 5 classes during its training and its learning phase. And then when you show it new things, you'll show it only new things, but you won't evaluate it on the old things that it might have forgotten, right? And this is not, and so many of the evaluations that are present in these sort of larger learning scenarios don't apply here because we don't want to show a model many examples of a pneumothorax and of you know, a hernia, all of these different things, a fracture, and then show it some COVID examples and then have it forget, well, what does a fracture look like? I don't remember. Additionally, we have these multiple labels, right? When you have one X-ray image, you could have a fracture and pneumonia. That's possible, right? And so you have these multiple labels that are toggled on. But very rarely is one object multiple objects. It's not both a dog and a cat, right? You don't have cat dogs that are coming around. And so I think there are all of these technical challenges where you can't just take off-the-shelf models or tools, algorithms that have been developed, because they're often developed in a setting, again, for natural images mostly, where we don't have any of these constraints. And so there's been a lot of work between the students and the postdoc that Joseph and I are co-supervising to try to understand how we can modify a lot of these meta-learning, few-shot learning, zero-shot learning algorithms so that they work in this setting.
Yeah, I think what strikes me from how you've described it is that COVID-19 is an entirely new phenomenon that we haven't seen before. So the old models, you can't just apply them. We have to really think about, you know, how do we modify them for this particular circumstance?
I think it's also, it's unclear for something like COVID-19, right? How different it should be, for example, in this one modality in chest x-rays from pneumonia, very severe pneumonia. Right. And so we know that in a lot of early cases, for example, in China and Iran, you would have COVID-19 cases that were diagnosed as just typical pneumonia, right? Which led to high mortality rates initially. And so it's unclear whether in this one modality, just looking at chest x-rays without any additional information, whether we would be able to detect a big difference that, you know, just one snapshot, we're not seeing any progression, we're not seeing anything else. Between a pneumonia case and a COVID-19 case, right? And so that's why it's so important that Joseph and his team have been working to collect other indicators along with just this image, right? So that we can see, for example, maybe it's not a one snapshot that you're given without any context that's important. Maybe you have to see some metadata. Maybe you have to see some progression.
Right. And so, you know, there's a lot of research. There's a lot that we're going to learn about COVID and its impact on people and their health, hopefully through this project. So you guys have both alluded to this a little bit. I want to talk a little bit about the fact that this is a new collaboration between your two research groups. So we've got a research team at the Vector Institute, supervised by Marzyeh. We've got a research team at Mila in Montreal, supervised by Joseph. And you've organized yourselves looking at different objectives and different projects. Tell us a little bit more about the team of people behind the scenes that are really at the front lines doing the day-to-day aspects of this research.
Well, I think we have a bunch of students that are specifically, I guess, Karsten, who's between both teams right now. So he's at Vector, but where he used to be at Mila. So he's really bridging the gap between these two groups. Yeah. So I think that's it's good for both labs in general to have that cross pollination there. Medical student Landau, who's we were working on evaluating Chester in some educational settings, and then we've shifted now to focus on how do we make this help treat the COVID cases, right? So in terms of figuring out with the radiology and medical community, like that they want severity prediction, right? And also looking at the trajectories of patients. So isolating those specific cases has been very useful, and I think it's a great opportunity for people that we have working from medical backgrounds to really look at the computational side of all of this and how it can assist these things. With collaborators at Stony Brook, students there are working on running these tools that we're building to kind of really analyze what they can do, what they can tell and inform these medical professionals and how that's going to actually get into their clinical workflow, right? At what point does a decision need to be made, and their insights into how that these tools, like if they can span the gap, span this chasm between the two fields, right? How can that workflow be disrupted by these medical tools, right? So it's just like an iterative process that has to keep going, and we need to make better tools better. But I think getting that feedback from students that span this boundary is very important.
So critical when we're computer scientists and used to, a certain way of working and a certain way of thinking and a certain jargon to work directly with the clinicians who are at the front lines, and they know what tools and resources and insights that they need you to help them find out of the data, but also really helpful to hear from them what their experience is and how AI can really help them in the course of their treatment of patients. Marzyeh, tell us a little bit about your team.
So the team that I have here, the way that this sort of percolated is I had a postdoc, so an NSERC postdoctoral fellow who was working in my lab previously. And then I had invited Joseph to come and give a talk in my class. So I have a machine learning for health graduate course that's taught in the Department of Computer Science. And I wanted him to come and give a lecture on medical imaging. And he came, and the students loved him. They thought he did a really fantastic job. And so he also had a chance to meet with some of my students while he was visiting the Vector Institute. And he had a chance to meet with my postdoc. And after he had gone, my postdoc, Lale, had said, he's great, you know, like it was really helpful chatting with him. And so she and I had been talking outside of the context of COVID, completely independently. Before this all hit, we had a project where we were looking at, and this paper is posted to archive. So we're looking at the differences in classification rates in chest X-ray images amongst people of different ethnicities, different genders in the United States, of different insurance types. And so there's a lot of exclusion, and there's a lot of difference in how accurate machine learning models are when you train state-of-the-art models, and how accurate they are in classifying people of different, again, genders, ethnicities, and insurance types on these standard tasks. And some of this is just because we have underrepresentation, right, of these in these data sets. That's the way that it is. And so she and I had done this project previously, which is currently under review, but also posted on archive if people want to read it. And then she had spoken to Joseph about this, and we were talking about ways to fix this, right? So, you know, we've established that there is this problem. We'd really like to fix it. And so then the COVID happened, and we discussed with Joseph, you know, really what we want to fix is this classification problem. Wouldn't it be nice if we were thinking about it in this robustness sense, right? Not just from a bias perspective, but just from overall robustness. And so she's led a lot of this on my team side. And then Joseph and I talked about how we really, and so Joseph has been, you know, on all our weekly team calls for a month and a half now, right? Like going through all of the planning for this project. But then Joseph and I had discussed, you know, we wanted to have an additional student, right? Somebody who really could do the extra bridging, because Lala was sort of, you know, part of my team previously. And Joseph has some students who are part of his team previously. So we wanted this additional person who could help with the bridging. And that is this student, Karsten, who's fantastic. And we've been meeting with for the past 2 weeks since his onboarding. And I think it is really important to have a mixture of people from both sides, right? So both people who, you know, have experience in different kinds of machine learning, experience on the clinical side, in trying to understand how you might scrape things best, how you might label things best, when there's a discrepancy between different sources of information, which one you should rely upon more. So I think that has been very helpful.
That's so great. And I love the idea of, you know, having somebody who bridges both teams in these times when we can't meet face to face and we have to meet virtually, having somebody who's going back and forth and interacting and really seeing both sides of the project very deeply. It's so helpful to sort of keep everybody together. Okay, so we're going to move to some audience questions now. And I've got a good one here that's come in. And so it reads, Joseph mentioned that a clear licensing policy is helpful when attempting to use a publicly available image data set. Could you speak a bit more about the features of a good licensing policy? What challenges do you face with licensing policies?
Yeah, so with a lot of data sets, there are very ambiguous licenses that they have. So for a subset of the data set we have that's come from EuroRAD and Radiopedia, which I really want to shout out to their groups, because their licensing is a Creative Commons non-commercial share-alike license, which is just great for the people want to contribute to do public research, right? So a non-commercial license makes everyone happy with that arrangement, right? Because if there's commercial interest, this can make people more hesitant to share. So having that non-commercial license is fine for doing research with, right? And then there's been a new data release that came over from Hanover University in Germany. This is just like a few days ago. And we just discussed with them, and they want to contribute their data to merge it into our data set. But they're going to continually do data releases. And they did like a Creative Commons share-alike, I think. Yeah, so it's just a Creative Commons share-alike. There's no non-commercial restrictions. It's even more open than the existing data we had, which is really great. So I think it just makes it easy to do anything with this data set. And I think that's really an enabling license. Right? So the licenses are more for the enabling aspect of it. And then for the epitome of open data sets, there's the NIH data set, which we can all, like Ronald Summers, 2017, kind of completely like broke open the entire field of digital or AI radiology, right? With this data set that it had it's like a public domain license. So it's very clear what you can do with it. You can do anything, right? And this has enabled us to make derivatives of it. And really, like Google has built a new data set, which is based on that data set, and they just relabeled it and then released that as a derivative work. And it's a highly accurate, really specialized data set. So like these derivative works are the result of a really good, clear license, right? That makes everyone happy with that situation and feel more confident that they're not going to have to take down this derivative work after they've released it, right? And we can already see that happening with the data set that we've released, right? Given the ability for groups to add annotations on top and then release that as a subsequent work, right? So we've had a group that's annotated the lung regions as bounding boxes and released that so it's now in our repository, released alongside our data. So they've kind of labeled a subset. We're in discussion with other people that are going to do even more fine-grained segmentations on the data we have, right? And I think that they're doing that because this data is open in the first place, right? So I think so the clear licensing makes it easy for everyone to work with and use for their different purposes, right?
Yeah, I mean, we know how critical data is. The foundation of what we do in AI. We couldn't do any of this without large, very accessible, very good data sets. So it's so important to have access to them. And I love what you've just described, Joseph, about how the fact that they're open means that other people are doing more and bigger and other interesting things with them. And in fact, it becomes a global collaboration when we're thinking about how other people are making derivatives and adding on to the work that you're doing. It really makes a very strong case for continuing around open science. Okay, so we have another question that's come in. Marzyeh, one question that came in from the audience was they're wondering if there are any applications on your AI-based approach that can help to inform the development of new treatments for COVID-19.
I think it's hard to know what this could be extended to. In terms of treatments, one of the things that has been really hard to hear from a lot of the local hospital specialists that I collaborate with on other projects, but are now sort of overwhelmed with COVID-19 treatment, is that many of our most intensive treatments are not working consistently, right? So there's been a lot of anecdotal reports, but now several reports coming out of other locations that were hit much harder, right? So this is out of China, out of Italy, out of Iran, out of New York, that mechanical ventilation is not working consistently. And that some of the pre-existing conditions that you might have assumed would have led to really, really poor responses, so comorbidities like asthma, they are not, right? And so I think that it's possible that a better detector, a better classifier for early screening, especially as we start to have conversations in North America about opening up, what that means for summer, what that means for the fall, whether there will be second waves that come in. I think it opens up the ability to have more maybe quicker screening or more physically distant screening, lower cost screening for particular populations. So I think it could lead to a better understanding and characterization. I think there's a lot of very good work on the biochemistry side being led by people like Regina Barzilay at MIT or Alan Asper-Guzik here at University of Toronto, who are trying to figure out exactly what's happening with specific drugs or treatments.
Great, thanks for that. We have time for just one more question. We're getting lots of questions coming in from the audience, so lots of interest in this topic and this project. One more question maybe for the both of you. How do you balance the need for fast-growing research and preprint publication with the rigor and peer review during the pandemic, right? So we want to get our results out. We want to share with the world, but it's, it's not the same thing as a peer-reviewed publication. So how do you balance that, guys?
So I think nothing should change, because why were we not being critical about the papers in the past? We just blindly trusted the peer review.
Right.
Yeah. So I think if a paper is hard to understand, and therefore, and for that reason, you can't like believe that it's right because you don't understand the entire experimental protocol, then don't trust the paper, right? Like, why should peer review allow someone else to tell you you should trust that paper, right? It's just more work to filter these papers yourselves. You should always be doing this with every paper that
and so how important is it right now to get your results out in the preprint world?
I think it's becoming increasingly apparent that the style of early release of results that is, I should say, you know, different academic communities have very different ways that they tend to push results out. And the machine learning community for a while now has had a culture of publishing a preprint on a service like arXiv, and then as it is undergoing peer review. And then you may see, for example, this is common, I just want to emphasize how common this is, that a paper is posted in September of 2018 on arXiv. It is submitted somewhere and doesn't make it into that particular machine learning conference, right? Unlike many of the journals where there's this, you know, year-long back and forth where, well, what, you edit this, cite this, add this. You have this one shot that is, you know, mildly stochastic, right? Depends on what reviewers you get. You often don't have a rebuttal in some of these conferences. And so you might submit to NeurIPS, and it doesn't get into NeurIPS. And so that's fine. You know, we say like re-roll, right? You submit essentially the same paper with some corrections or clarifications as recommended by the reviewers to ICML, or to, if it's more data science focused, to KDD, to, you know, wherever you're submitting it to, right? So I don't think that culture should change. I'm happy that other publishing cultures are coming more in line with that. I think that that puts significantly more, a much higher expectation of rigor on the PI.
Indeed.
So my student, one of my previous students really wanted to archive their work because they felt some pressure. And I told the student, it's not ready. And they said, why? It's not peer reviewed, it's just arXiv. And I said, no, like this is
ready to go. Yeah.
It has to be ready to go. This has to pass my sniff test because it has our names on it. And it means that we are putting this out there for consumption, and you don't want to mislead people. And so I think that it shifts the burden from a, well, let's just throw this out to peer review, we'll see if they spot a mistake, to saying like, this is an academic product that I am approving as I think this is good enough to go out there.
Thank you so much to both of you for sharing your insights on your project, and also the inner workings of the machine learning community, the academic community, the research and publishing community. We are over time. I have to apologize to our audience for going a little bit over time, but the conversation was so interesting. I wanted to let everybody know that this is a series that CIFAR is offering, and we have another webinar just like this coming up on June 4th with a fellow in our Humans in the Microbiome program. His name is Professor Hendrik Poyner. He's from McMaster University, and he's going to talk about what makes this pandemic, he's an evolutionary geneticist. He's going to talk about what makes this pandemic different and what we can learn from past pandemics to inform us about what we know about COVID-19. So it should be very interesting, and we hope that you can join us then. So please visit our website, cifar.ca, to find out more about the upcoming webinars. We'll have the video for this one posted next week, and we'll look forward to seeing you again. Thanks once more to Marzyeh and Joseph. Bye-bye.